Today I'm going to give you a deep dive into the hype behind quantum technologies and give you an overall understanding on how they work and why are they in the news constantly. Why do scientists and researchers think they're so important and might make such a big difference for the future of computing? So the main difference between quantum technologies and classical technologies is the actual information they work with. In classical technologies, we work with bits. So these are those zeros and ones that you constantly see in movies. You can think of them as a light on and off. And basically, to encode information, we program series of zeros and ones that have certain meanings. For example, you might have binary systems in which a series of zeros and ones is equivalent to a specific number or to a specific letter, and your entire computer is basically just storing and manipulating these large quantities of zeros and ones that are encoded into its memory in order to do everything it does. In quantum computers, for quantum technologies, that information is encoded in a qubit. Now, a qubit can be either a physical object, kind of like an atom, like an actual real thing, or it can be an artificial version of one of these real things. Qubits are quantum bits of information, essentially. They are really, really small and they're really, really difficult to manipulate, and they're really complex. So they are encoded in this three-dimensional sphere that is called the Bloch sphere. That showcases specific states. So I know that sounds like, a lot of lingo, but I will break it down slowly. So a qubit basically is a position in this three-dimensional sphere, so this little dot here, that can be encoded by its position, right? We can see angles with respect to the x-axis that exists in the Bloch sphere, and our qubit is basically defined by a wave function. It can be manipulated going through gates. That is the exact same thing that happens in the classical world. So you can change or modify your qubit by making it go through these gates, and you can also measure it. When we measure a qubit, we collapse it back down to a bit. So actually, we only have qubits for the period of time in which we compute, in which we manipulate them, but to actually read them out, we break them back down to bits. That can look a little bit like this. You might have one photon that goes through a series of half-wave plates, so of manipulations, and then is detected. And when we look through our detection apparatus, we just literally see zeros and ones. An alternative qubit could be an atom. So as you might remember from high school, atoms can be excited or grounded. Most atoms, all atoms kind of start off in their grounded state, and then they can be excited by injecting energy, so by pointing a laser to them essentially. And, this excitement and disexcitement of atoms actually produces photons that we can visually see. Like you can actually see the atoms, lighting up. And that's kind of how neutral atom computers work. This is Inflection's quantum computer. You literally just see dots that are lit up or not, depending on wherever they are in the 1 or in the 0 state when they are read out as bits. Now, one of the main things that qubits can do that bits cannot do is be in this three-dimensional Bloch sphere. So for now, we've kind of said, well, depending on where we are in the Bloch sphere, that can be defined by these angles. And, the reason why we care about the positioning in this Bloch sphere is because the closer you are to the poles, so to your 0 or to your 1, the more likely you are to collapse to that state, to the 0 or to the 1. So qubits are probabilistic, they're not deterministic like bits. So if you get a 0, you have a 0. In a qubit, up until the moment you measure it, you basically have a probability of collapsing into your 0 or to your 1 state. And depending on how to the north or to the south you are, you're going to be more or less likely to do that. If you're in the middle, well, it's a 50-50. Now, that makes sense when we think about, the outer bit of the Bloch sphere, but it's really encoded in 3 dimensions, which means that it can be a little bit inside of the Bloch sphere. And the way you create these qubits that are inside of the Bloch sphere instead of on the outside of the Bloch sphere is by entangling them. So, we've already talked about having one atom by itself, it's excited, but what we can do is excite multiple atoms or multiple qubits together in the same wavelength and create quantum correlations between them. This sounds very science fiction-y because it kind of is, but essentially what we're creating is pairs of entangled qubits, which can be photons. And these correlations, these entanglements, they don't have any classical, equivalents. We can't really recreate them in the classical world. They exist in the quantum mechanical world, in the world of the very, very little. And what they mean is that if we look at two qubits which are entangled, and we measure one and we obtain some information about one, then we will know some other information about our second qubit. So in this case, if we measure our qubit 1 and it is red, we will know that our qubit 2 is blue. And if our qubit 1 is blue, we'll know that our qubit 2 is red. This correlation actually has no distance limitations. We can be in two opposite sides of the universe, and this will work. And not only that, but we can actually chain these correlations. So we can have, qubit 1 be entangled with qubit 2 be entangled with qubit 3, and that will mean that qubit 1 and qubit 3 are actually entangled. We can chain these up, which kind of is very neat, because if for the people who are already kind of familiar with the networking world, with the classical networking world, this is kind of sounding really nice for connectivity and for communication, right? We have these correlations that we can manipulate, that we can look into, that we can create, that have absolutely no problems with different distances. I mean, it's starting to sound like a really good base for an internet of our network. Now, if you're not from the networking world, you might ask yourself, why? Why does this make sense? Well, there is this thing called communication complexity, which basically is boiled down to asking yourself, if I have, a series of people in a situation and they want to send a message to each other, what is the minimum amount of information they need to send each other, the minimum amount of bits they need to send each other in order to, solve the problem or the situation they're in. And they're kind of like competitions in computer science, and they have limits, the baseline limits of how little information you can send from one player to another in order to win a game. And there are, thousands of these problems, and quantum technologies are actually pretty good at solving quite a lot of these problems. I mean, here's a list of some of the ones in which they've already shown or demonstrated advantage. Well, let me walk you through an example. I think if we walk through an example, it might become a bit clearer. We're going to walk through superdense coding. So superdense coding is this problem. As I've said before, we're talking about problems where we've got players. So we've got two players, Alice and Bob, and they want to send Alice wants to send two classical bits to Bob. And that would require sending two classical bits. So that can be 0, 0, that can be 0, 1, 1, 1, whatever. Now, to send two bits, you need to have two bits and to send them. But if you have a quantum network, you can be fancy. And we're going to assume we have a quantum network. And in our quantum network, we kind of almost always assume that Alice and Bob share an entangled qubit pair. So, this pair that's been already entangled, it's correlated, and it's been pre-shared. So Alice and Bob met up in a place, they both got one of the qubits in the pair, and then they went their separate ways. Now, this means that if Alice manipulates her qubit, it will also change Bob's qubit. That's the whole point of the game. So what she's going to do is she's going to apply one of 4 qubit gate combinations to her qubit. That's going to generate one of the 4 Bell states. Not too important what any of this means. I mean, essentially, she's going to choose one of these 4 options, and that's going to be equivalent to her sending one of these combinations of qubits if Bob receives both qubits. And then what she's going to do is she's just going to say, well, you've got your qubit's already been changed because mine has been manipulated, and that's the whole point of them being entangled. Then I'm just going to send you my qubit, and I'm going to claim that, well, in the classical regime, I had to send 2 bits, but in the quantum regime, I get to send 1 qubit, and you can basically decode the same information. Now, obviously, in the current world, in the real world right now, sending over 1 qubit and maintaining this entanglement is way more expensive than sending 2 bits. But in the information theoretic context, like in the actual math, you could very easily argue that this is a much cheaper trade-off. You're sending over less information. Now, we made a few assumptions in order to make this problem work. One of them was that we assumed we were working in a noiseless environment. So one of the biggest issues for quantum technologies is noise. So if we go back to our atom, right? Our atom can be either grounded or excited, and the whole idea is that we manipulate the state via sending a laser to it and exciting it. But there's more than just the wavelengths of a laser that can be, affecting this excited and non-excited states. There's, microwaves all around us. There's going to be noise in labs. There's going to be people walking around. And all these things kind of make these quantum mechanical states that are incredibly fickle and incredibly easy to manipulate, really unstable in a sense. I mean, that's why when we think about a quantum computer, we actually think of these massive fridges that fall down from the sky that are basically bringing down the tiny, tiny chips within them back down to like almost absolutely 0 degrees. We're really trying to, vacuum seal and freeze these chips to try to avoid having any of this noise. And then there's also the entire field of error correction that is, based on this idea of trying to encode many physical qubits into one logical qubit in order to be able to, minimize the effects of noise. Another assumption that we made is that Alice and Bob had also, pre-agreed on the measurement basis prior to any of this. So when you look at our sphere, there are different ways in which you can look at our sphere, right? You can look at it, from the top, from the bottom, from the back, in front. There are positioning arguments to how you could actually measure the sphere. And that is called a measurement basis. You can usually think about it in like either the X or the Y axis. And it has an effect in the actual state, in the actual bit that you get at the end when you measure it, because it's not the same to look at it from the side that from the top, right? So you need to agree to look at qubits from the same measurement basis before measuring them in order to get the same information. Now, these are things that are kind of reasonable to assume, but if we wanted for Alice and Bob to have this information and they were never in the same place, they were like two computers that are separated, they would kind of have to send this information. One of the ways in which they can send this information is just through a classical channel. They can just say, hey, listen, we both agree, we're gonna measure in the X basis, and we both agree that like we have no noise, we're not evil, we're both gonna be like super sincere about what we're doing. But what if there is a malicious agent? What if we're trying to break into a quantum network? And that kind of leads into the second phase or into second area where quantum computing and quantum technologies and quantum networking are like a really big thing. It's security, right? Everybody talks about how safe quantum technology might be compared to classical technology. Let's kind of get an intuition on why they might be talking about that. So the quintessential quantum security protocol is QKD, quantum key distribution. I'm just going to walk you through the protocol. The idea is that Alice and Bob are trying to share a key of information without getting tapped into. And they're going to do this through a series of steps. So Alice is going to first prepare and send a bunch of qubits. They're going to be prepared in completely random basis, and she's just going to save in her memory what basis she was using to prepare these qubits. Then Bob is going to get all these qubits and measure them himself in completely random basis. And then they're going to both publicly just announce what basis they were using for their measurements. Now, as you remember, when we measure a qubit, we collapse it back to a bit. So when they are claiming these bases, they've already measured everything. There's no qubits in communication anymore. They've looked at everything. And they have this massive series of all the bases and all the qubit states that they've received. And the idea is that they are going to basically throw away any qubits where the bases don't match, where one of them, has prepared in one basis and the other one has read it in another. That doesn't work. They're just going to keep the other ones. And they're going to estimate the error rate that they have between what Alice generated and what Bob got in order to see how safe their communication is. Now, that sounds very weird. So let's walk back a little bit. We've got a malicious agent, Charlie. Charlie kind of has two options. The first option is they can try to tap into the classical channels. If they tap into the classical channels, they can't do anything really at all, because the qubits are already collapsed, and that's what the information that was being sent actually is. It cannot interpret anything. It cannot learn anything about the qubit states, because like having a series of bases is not really useful once the qubits aren't there. If it tries to tap into the quantum channel in order to retrieve information, there's a few options. So option A is that it's just going to tap into the quantum channel. It's just going to look at the qubits that it wants to look at. Obviously, that will mean that the qubits will collapse. And when it comes down to Alice and Bob sending each other, their list of bases, Bob's bases is going to be, list of bases is going to be shorter because he'll have received less qubits, and therefore they'll know something is wrong and they'll cut it all off. The second option is that he decides to replace the qubits, right? So they need to do this before A and B share their classical bases, otherwise we'll be in the same situation. And that means that they need to kind of do it before knowing the bases. If we wind backwards for a sec, the idea or the thing that they're trying to break is that, Alice and Bob are trying to estimate the error rate of their communication. So they're really trying to not inject any errors because otherwise they'll be detected. And if they just send in a random bit, they're obviously gonna bring in more errors than if they knew what the bits were, and they're gonna get detected because Alice and Bob are assuming that there's not really any major noise going in. So if they're just sending in random qubits, it's not gonna be consistent. Whereas the smart thing would be, well, take in your qubit, look at it, and replicate it. Send in an exact copy. Unfortunately, quantum mechanics, or fortunately for Alice and Bob, quantum mechanics comes in with this massive, rule that says that it is impossible to create an identical copy of an arbitrary unknown quantum state. Charlie does not know their quantum state, so they cannot create a copy of it just like for real, mechanically they cannot. What they can do is, try to learn the quantum state. They can try to measure it and try to replicate it. The issue is that when they try to measure it, they're going to have to choose a basis. They have a 50-50 chance of getting the right basis because there's the two options that I showed you earlier, right? So they basically are tossing a coin over many qubits. And unfortunately, that noise will be detectable by Alice and Bob because basically what they're going to do is they're going to reveal to each other a subset of their accepted qubits, accepted bits, basically. And they're going to notice that the error rate is way higher than what they theoretically expected. Things are obviously being tapped into, and they'll know that things aren't safe. So in a sense that you could say that, when you're looking into these quantum channels, you can detect if somebody's there. It's not exactly true, but you can think of it that way. Now, beyond security, beyond reductions in, communication and the cost of communication, which is, a huge thing, especially in our currently super interconnected world, there is the idea of computational advantage. So I was, trying to make a slide for this presentation and trying to find some news about, some country deciding to invest in quantum computing a crazy amount. And literally an hour ago, the Chancellor in the UK pledged £1 billion. So I thought, oh, this is perfect. So there's all these countries, there's all these companies that are pledging so much money to building this technology, especially in the context of computing. And the question is why? Why do people care? I mean, there's a communication complexity reduction, sure. There might be security advantages, sure. But this only makes sense in the networking sense. It doesn't necessarily make sense in the computing sense. Well, one of the first reasons is emulation. So there are two things that you can do with computers. Well, there are more than two things, but you can simulate systems. You can kind of imitate and mimic and pretend to replicate a system in order to study it, or you can basically reproduce it, like copy it essentially and remake it completely. And quantum mechanics, quantum physics has a lot of open questions, and it's just a great idea to kind of try to solve them via experiments. And quantum computers are kind of the best way to experiment with quantum states because they are quantum states. They're made of quantum states. Now, this is interesting for physicists, but what about computer scientists? Well, computer scientists, again, they care about complexities. They care about how much time, how much memory things are gonna take. And there's a series of quantum algorithms that basically showcase advantages in complexity compared to classical algorithms. One of them is a Deutsch-Jozsa algorithm, which basically tries to solve the following problem. You've got a black box, an oracle. And this oracle, you can give it a series of inputs and it will output either a completely constant output, so always give you zeros and ones regardless of what you give it, or it will output a balanced set of outputs, meaning it will give you 50 ones and 50 zeros. If you wanted to do this with a classical computer, your query complexity would be 2 to the n plus 1. And if you wanted to do this with a quantum computer, your query complexity would be 1. What does this mean? Well, for you to know that you're going to get, you have a situation where you didn't get really unlucky and, your first 50 options were 1 and then your 51st was also 1, but you only checked the first 50 and you assume that it was a 50-50 and therefore it was balanced, you're going to have to check for more than half of the output. So you're going to have to check half of the outputs. So your inputs are n, your outputs are also n, and you're going to have to check it plus 1. That when we, write it in complexity annotation, it gets summarized down to the n, but basically this is, you have to check half of the things plus 1. But if you have a quantum computer, what you can do is be really tricky about this and basically put all your inputs and therefore your outputs in like a superposition. You basically correlate them all, and then you just check a global property. You check if they're all in the same phase. So you can think of this as like kind of wave functions collapsing together. If they're all in the same phase, you're gonna get 1. If they're all, if you've got half and half, they're basically gonna, it's gonna be plus 1, minus 1, plus 1, minus 1. So your total is gonna go down back to 0. And you're in one query, you can see if all your things have the exact same constant or if you're in a balanced function. And you can answer the question in one query. That's pretty much the TLDR of it all. Thank you.